So our topic today is the method of U-substitution to solve integrals. And this is, like I mentioned earlier to you guys, it's a really, really important topic, mainly because perhaps this is the one topic you're going to use most in Calc 2 out of Calculus 1. It's like it's going to be used like from day 1 till probably the first several weeks, and then when you get to Calc 3, you're going to use it again. When you get to differential equations, you're going to use it again. So it's extremely important to have a good understanding of this method in Calculus 1 in order to be successful in those other classes as well. Now the idea is the following. This is like reverse chain rule in a sense. You know, how do you integrate something complicated like 5x plus 1 to the third? Obviously, one method would be to multiply 5x plus 1 by itself 3 times and then integrate it one piece at a time, which would be very boring, very tedious, and I'm sure every one of us would make a mistake along the way. It's just so long. Luckily, we have U-substitution, which will give us a shortcut method. You don't have to multiply it out. And here's how it works. First, you let U be equal to a quantity. So let U be, in this case, 5x plus 1. I'll give you more information about how to pick your U in a little bit. At the moment, let's just pick U equals 5x plus 1. The idea is the following. You go from an integral in terms of x to an integral in terms of U, but it should be an easier integral. Okay, so like for example, if I come over here, instead of 5x plus 1 to the third, what can I write? U to the third, right? U to the third. But here's the trick. You cannot just put dx back again because dx goes with the 5x plus 1 to the third. You need to get rid of the dx as well. To get rid of the dx, this is what we do. We come back here. If u is equal to 5x plus 1, what is du dx? What is there at the right-hand side? 5. So notice, even though ultimately we're going to be doing integration, as the intermediate step, we're doing a little bit differentiation, as you can see here, to find du dx. Why did I find du dx? Because I need to know what dx is in terms of du, because I need to get rid of this dx over here. So let me write it like this. Again, this may look a little bit weird because we've never done it like this, but you can write that du is equal to 5 times dx. Du equals 5 dx. So from here, what can you tell me about dx? Du over 5. So our goal is to write a new integral over here that only has u's in it, no x's. So instead of dx, I'm going to write du over 5. And while I'm doing that, I can take the 1/5 outside. By a property of integrals, the constants can be pulled outside, as we have seen. Now, does this look easier to you? Wouldn't you rather integrate 1/5 u cubed du instead of integrating the first integral? Right? It's much easier. You don't have to multiply, expand the cubic expression. So now let's integrate it. What is the integral of u cubed? That's very easy, right? 1 over 5 times u to the 4 over 4. And if you don't have limits of integration, we always put a plus c at the end. But here's the problem. The given question did not have a u. We brought the u in, and it's our job to get rid of it at the end. So what can I put instead of u here to get rid of that? Whatever you set it equal to in the beginning, right? 5x plus 1. So instead of u to the 4, I should write 5x plus 1 to the 4th. By the way, did everybody see how I got this 20 here? I combined the two fractions in the previous step. 1/5 plus 1/4 is 1 over 20, right? So I put that up front. And I left the answer as 1 over 20 times 5x plus 1 to the 4th. You could also multiply c by the same constant, but any constant times another number is still another constant, so you don't have to worry about that, but it's a good question. How can I check this answer? Take the derivatives, right? So let's check this. Take the derivative of this and see what we get. The derivative is 1 over 20 times. Who can tell me what I should write next? I'm differentiating now. Bring the 4 down, right? It's been a long time since we did derivatives, so it's natural if you're kind of feeling a little bit rusty right now. What power should I have? To the 3rd power. And by the chain rule, I should multiply everything by what? 5, which is the derivative of the inside, right? Now, 5 times 4 is 20. 20 over 20 is 1. Did I get back what I started with? I did, right? 5x plus 1 to the third, 5x plus 1 to the third. So it works, and it saves us a lot of time. So let's do another example to show how U-substitution can be used. Okay, here we have so I ended up erasing it a little bit when I came down here. But what should it be? Let me rewrite that. But what is the correct answer there? Because you multiply everything by the derivative of the inside, right? Derivative of the inside is 5, and then I cancel. That's why it kind of looked a little bit like a 3 later on. Okay, but it was a 5, and then 5 times 4 was 20, and 20 over 20 they canceled. Okay, and do you see where the 5 came from once again? Yeah, but from the chain rule. Sure, but it came from the chain rule, right? Okay, next question. My integral seems cut off there. Let me make it a whole one elongated s. Okay, I want to integrate this function. Now imagine not having to use substitution. You would have to multiply this thing 5 times by itself, then distribute your x all the way over, then integrate term by term. Practically nightmare situation. It would be like impossible. It's not impossible, but very, very tedious. How can we do it instead with the U-substitution? Okay, so let U be something. What do you think we should select for U in this case? Now, it's a good guess. I haven't yet told you the rationale as to how you should pick your U, but in general, here's the rule. In general, choose U in such a way that its derivative is already in the given integrand, that its derivative is already existing. It's already in the given integrand. Integrand is everything within the integral sign. That's called the integrand. So it's already in the integrand. And I'm going to say up to a constant. You never have to worry about constants, because constants we can always multiply by, divide by. We can get rid of constants up to a constant. So choose U in such a way that its derivative is already existing in the integrand. For example, if we go with Ryan's suggestion of letting U be 3x squared plus 4, what is the derivative going to be? 6x dx. Don't worry about the 6 part, but the x dx. Is there already an x dx in there? Yes, then you know this problem can be done with U-substitution. If there had not been an x dx there, we cannot use U-substitution. You have to wait until Calc 2 to learn other techniques to solve that problem. Okay, so basically just know that every question that you have in this section under U-sub, you will always be able to pick a U with this definition, with this selection technique, because they want you to practice U-substitution. So every question they will give you, you will have a situation like that. Okay, so in the next step, this quantity can be replaced by what? U to the 5, or U to the 5th power, exactly. And what about x dx? Now let's wait on that for a little bit until we differentiate the U, right? So we come down here. What is du dx? 6x. So that means that du equals 6x dx. And I want to show you something. From this point forward, I'm not going to write that middle step there where I write du dx equals 6x. Instead, when I have u equals 3x squared plus 4, I'm going to write in the next step du equals 6x dx. That's a very common procedure. You know, when you take other math classes from other instructors, chances are that's how also they're going to do it. If you don't feel comfortable yet, put that extra step in there, but ultimately try to get to that step from the u. It will save you some time in the future as well. So I look back to my integral. What I'm missing is the x and the dx. So what is the x dx from this equation? what is x dx? Because that's what I need. I need an x dx written in terms of u based on my equation. What is x dx? du over 6. Now, there are different methods to solve this integral. One is what I just did, du over 6, and I put the 1 over 6 outside. Another one, some students like to do it this way. They always solve for dx. So they replace the dx separately. Then they come back, they see an x. OK, I'm going to also solve for x. But I think that's tedious. It's easier if you look at your integrand and say, OK, what do I need? I need x dx. And come here and solve for what you need. In this case, it was x dx. That, in my opinion, is a more direct way. OK, do we know how to integrate u to the 5, u to the 5th du? Do we know how to integrate that? No problems there, right? U to the 5th is going to be easy to integrate. Yes, Daniel?
How come this one, like you were able to take it to the fluid, there was no x there?
OK, but because our u was 3x squared plus 4, its derivative was 6x dx. What was the u in the previous question? 5x plus 1, its derivative was 5 dx. So we were OK on that one as well, OK? It depends on what u is as to what else you're looking in your integrand. OK, like if, yes, up to, like if you use x cubed, you want an x squared in there, etc. OK? Yes, exactly. Basically, every question will be a little bit different in that regard. OK? So how do we integrate now u to the 5th? U to the 6 over 6, right? So plus c, of course. So now we have u to the 6 over 36. And remember the last step. What should I be doing here? I don't want to leave the answer in terms of u. So put back what u is in terms of x. In this case, it is 3x squared plus 4 to the power of 6. Again, you can check this, but I'm not going to check every question. It's actually a good exercise if you have some time when you do the homework to do the checking, because it's kind of preparing you towards a final exam where it's a little bit cumulative, as you know. Of course, there will be some differentiation questions. At this point in the course, it's good to be reminded of differentiation also. OK, any questions about this before we solve another U-sub example? Any questions? All right. Questions? OK, let's take a look at this one. I'm going to clean it up a little bit. Again, think about what would make a good choice for you and see how far you can get, and then we'll do it together in just a few moments. Again, I choose u be x cubed plus 1. Its derivative is 3x squared dx. First, the square root of x cubed plus 1, I'm going to write that as, you tell me, what can I write this as? In terms of u, that would be u to which power? U to the 1/2. And then the x squared dx, from here x squared dx is going to be the same as du over 3. I can put the du in and the 1/3 outside. So now I have 1/3 times the integral of u to the 1/2. What is the integral of u to the 1/2? U to the 3/2 over 3/2, or times 2/3, right? So now we have 2/9. And remember to replace the u back, right? U being x cubed plus 1 to the power of 3/2 plus c. Okay. Again, we're going to do quite a few examples of these. Each question is slightly different, but still, again, I want you to go really strong to your calculus classes with being very proficient at solving U-substitution questions. Any questions about this example before we try another one? Yes, Daniel?
1/3 come from again?
The very first 1/3, yes. That came because if you solve this for x squared dx, what is x squared dx? Du over 3, correct? That's where it came from, yes. Any other questions? Did you have a question? No? Okay. Let's do another example. As a matter of fact, I think we're going to do this in a minute, but I want to add one more before that one. Give me 1 second. I think I want to add, let's do this one. The integral of 5x over, maybe it's my next one. Let me check if it's not here. Okay, here it is. At the moment, don't worry about the limits of integration. Assume they're not even there. Let's do the integral of 5x over quantity 4x squared plus 6 to the 3rd power. Okay, so for this question, I'm going to let u be 4x squared plus 6. And the reason is because I know I can look at it at a glance. The derivative I know is 8x, and there's already an x dx on the top, so I know I'm in good shape. The 5, it doesn't matter. I can take the 5 out. The 8x dx, the 8 doesn't matter. I can always divide by the 8. So just do that quick check to make sure the derivative is already in the integrand up to a constant. So I know now that du is going to be 8x dx. And going back to the original integral, at the moment I'm ignoring the limits. The 5 I can take outside. The bottom is the same as u cubed, right? And what about x dx? From down here, x dx is the same as du over 8. So I need to put that then inside the integral sign, du over 8. Because the 5 has been factored outside, and the x dx is going to be replaced by du over 8. Okay, how do we integrate this? A lot of people, I think, forgot how to integrate something like u to the minus 3 du. What was the general antiderivative rule? You add 1 to the power and divide by the same power, right? We do exactly the same here. If you add 1 to the power, what do you get? U to the negative 2. Divide by the same power. Also, then you have negative 2 on the bottom, plus c. And I'm going to get rid of the negative exponent and multiply the constants. Negative 5 over 16. And u squared at the bottom. But instead of u squared at the bottom, let me just put its equivalent. Since u was 4x squared plus 6. Now, normally you would have a plus c there. But if you have limits of integration, once you've done everything, you put the u back, you get the x's back. At this point, you can say, okay, my limits were, by the way, from 0 to 2. And there you don't need the plus c, because if you have the plus c, You're going to have plus c when you plug in the upper limit, and then minus c later on when you plug in the lower limit. The c's would have canceled anyway, so you don't need the plus c when you have definite integral. So at this point, you would just plug in the numbers for x. And one thing you can do is if there's a constant like negative 5 over 16, you can take it outside of the whole deal. So that leaves you with like 1 over that quantity. Plug in a 2. So let's see, 2 squares 4, 4 times 4 is 16 plus 6. Looks like I'm getting 22 to the second power, minus, plug in a 0, and that'll be just 6 squared or 36. So again, I took out the negative 5 over 16, and then I'm plugging the 2 into the remaining expression. When I plug 2 for x, I got 4 times 4 or 16, and then plus 6 was 22. Had to be squared. Minus, I plug in 0 for x, I got 6 squared on the bottom, or 36. Now let's see what all of this simplifies out to. So I'm getting a very small answer. Anybody got something? Basically, at this point, you're just going to punch them into the calculator and get a numeric value. Just be careful, to put, like, I would personally what's in the parentheses and then multiply by negative 5 over 16. So I'm getting here 0.008 roughly. And if I want to check this answer, last time I showed you a command on the calculator. What command was that? FNINT, right? You enter the function that you're integrating, comma x, comma the lower limit, comma the upper limit, and that's a good way to be able to check the answer. I'm not going to do it because I'm running out of time today, but if you're interested later on, you can always try to check your answers using this command. But please be completely aware, I need to see every step of the way to work, otherwise, obviously, there's not going to be credit for getting it just on the calculator. Okay, and let's do this one before we go to the groups. The question is 3 cosine x divided by the square root of sine x dx. What is the integral of this quantity? Again, please take a moment to think about it. So if we let u be sine x, its derivative is cosine x dx, right? Could I have let u be cosine x here? Derivative of cosine is negative sine x dx. There's a sign here, but it's on the bottom under a square root sign, right? So that would not have worked well. You need to let u be sine. So its derivative is cosine x dx, and you already have cosine x dx in this integrand. So my bottom should be what? The square root of u. And the top, after I took the 3 out, I need cosine x dx. That should be the same as du, right? The question is, how do we integrate this? If you rewrite u as root u on the bottom as u to which power? Negative 1/2. We brought it up. So we have a negative exponent there. And now we need to integrate this. Any questions up to this point? Any questions? Yes, please. The 3 was in a given problem. I just factored it outside. You see that was 3 cosine x? du replaced cosine x dx. This is what du was, but the 3 was still sitting there. So du is cosine x dx. Any other questions? Okay. So now let's apply the antiderivative rule. Add 1 to the power. Negative 1/2 plus 2 over 2, you get positive 1/2, right? Divide by that power. Divide by 1/2. That's like multiplying by 2 over 1 plus c. So I have 6 times u to the 1/2, but the 1/2 power means square root, and u is the same as sine x, so I might as well leave it like this. Again, this is going to be pretty easy to check. If you have the time later on, please go ahead and perform a check on it.